Hello students, welcome back to the class. So we will be today continuing with our structure of atom. Disclaimer, the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So our objective will be very clear. So we will be continuing with this objective, which is covering the Thomson, Rutherford, and Bohr's atomic model. Our today's subtopic would be, first of all, we will see the atomic spectra. Second, we will see what is Bohr's model for hydrogen atom. Third is explanation for the line spectrum of hydrogen according to Bohr. Then third is limitations of Bohr's model. So these are the topics that we are going to cover today. So before moving on to the atomic spectra, you must understand what is a continuous spectrum. So if I pass a white light through a prism, then we will see that there is a spectrum of light that comes out from the prism. Now it is seen that the wave which has a shorter wavelength, they are bent more. They are bent more as compared to the one which have a longer wavelength. So we know that our white light is comprised of various colors which fall in the visible region, and since it is having all the light in a continuous manner, so we called it as a continuous spectrum. Now we can see blue color merging into the green color and green color merging on to the next one, and these things goes on continuously. So we call it as continuous. Now let us try to understand what is emission and absorption spectra. So this is a diagram for you. Now if you see that there are two diagrams here. First is A, in which there is an excited sample which is delivering some light. In second, we have a white light source. First, let us try to understand the white light source. So suppose we have a metal or a non-metal or any other element that in whose spectrum we are interested in. We keep that sample here. Okay. Now what we do, we take a source of white light and radiate this white light or throw this white light on this sample. So we have already seen this thing, that the energy is quantized, means it can only absorb a certain frequency of light. Rest of the part will be passed through this absorbing sample. Okay, so that rest of the part is allowed to pass through this thing and then it hits a prism. Now you can see in the detector, so this is the image of detector. It's very clear here that there are black part and there are colorful part. Now this black part is indicating that this specific part of the total spectrum, which is simply a collection of 7 colors. So out of those, this black part is being absorbed by the absorbing sample and rest of it is there on the detector. So this spectra that you get after the absorption of a part of light by the absorbing sample is called as the absorption spectra or the absorption spectrum. Now if I look at the image A, then the opposite of this image B is done here. So if we take this sample which has absorbed some amount of electromagnetic radiation and keep it here. Now since it has absorbed some amount of light, so it is in the excited state. So to stabilize itself, it will come back to the ground state, and in doing so, it will emit electromagnetic radiation. Now again, this electromagnetic radiation is allowed to pass through the prism. So you can see that this part, which is blue in color, was absorbed from the total spectrum. So that thing is being displayed here. Plus some black lines, you can see it in the middle. Okay, there are some black lines. So those parts were also absorbed by the sample. And upon emission, they are being shown here and there. Okay. So this is the basic idea behind the emission spectra and the absorption spectra. So this is what emission, because here the sample is emitting light and that thing is being detected with the help of prism. Whereas in the second case, our sample is absorbing the light. I guess it is clear to all of you, the part emission and absorption spectra. Now if I compare it with the continuous spectrum, then what will be the difference? So in both emission and absorption spectra, you can see some part that is missing, that are black in color. But in continuous spectrum, you will see all of the colors in the detector. There will be no black spot. Now this spectrum word is coming again and again, and I have already explained it, but I am telling it once again. We can just think it as a collection of electromagnetic radiations where we have various wavelength and frequency. Okay. Now moving on to line emission spectra. So we have already seen what is emission spectrum. Now we will look this emission spectrum for a specific sample. So it is seen that the emission spectrum of the atom in the gas phase, they do not show a continuous spread of wavelength. Okay. So rather than that, they emit only a specific wavelength. So the previous one which we have seen, there was still a band that was present. There were multiple colors apart from blue that were present. But in case of the line emission spectra, there are not a bunch of colors, but a specific color that is being seen. Now how this line emission spectra is obtained? So it is simply the emission spectra of the atom in the gaseous phase. So that thing is called as the line emission spectra. Or you can also call it as atomic spectra. Now this line emission spectra are very important because every element has its own unique emission spectrum or own unique atomic spectra. And the great thing is that some of the elements were discovered using this atomic spectra. So anyone has any doubt till this point? So I guess, so I will repeat this all of this once again. Okay. So I think you were able to message till now. So I will explain all of this to you. Okay. So just listen it very carefully. So two things are there. First of all, before understanding the atomic spectra, you must know that what is emission spectra and absorption spectra. Okay. Suppose you take a iron metal. Okay. You take a piece of iron metal. Got it? Now you take two prisms. So here is your first prism and here is your second prism. You take white light. Okay. Just pass it through the prism. what you will see? You will see a variety of colors. Okay, a variety of colors emitting through this prism. Since it is a white light, it will consist of various colors. Now, what will be those colors? So they will be red, blue. So each of the light that is present in a white light. Now, one thing is very important. If you see here, then first of all, we will see the red light. Okay. Then what we will see? Then we will see the yellow. Okay. Before that, we will have an orange one. Yes, very good. So that thing is called as Vibgyor. Okay, violet. So I'm not representing each of them. The one which I have here, I'm representing those. Okay, you have a yellow here. Now, you have a green here. Got it? So this is violet, this is red. In between, we have various different colors. So you know this thing very well. Okay, very good. Now, this violet light, this light is being bent more. Okay, as compared to other lights, this light is the most bent one. Whereas the red light is the one which is reflected very less, in a very less amount. Why is it so? And it has a direct application also, that it has been seen that it is used in ambulance sirens. The reason behind it is that it is not dispersed easily and can be seen from a large distance. Okay, so that is the reason it is used in the sirens and all. Now, if I ask you which has a greater wavelength, so this has the greatest wavelength. Okay, so moving from here to here, wavelength increases. Got it? And on moving on down, frequency increases. Okay, any doubt in this part? Till this part, if you have a doubt, you can ask it. I guess it is very clear. The spectrum part. So this is called as the spectra. Okay. Now what we do, we take this white light, we take a prism, but before moving on to the prism, we make it pass through a sample. Now that sample can be anything. So basically it is used in identification of an element. You take an element, you don't know what is that element. If you know the atomic spectra, you can predict the element, because their atomic spectra has been recorded and they are in the textbooks. So if you know the spectra, you know the element. Now what we do, suppose we take iron metal here. We are taking an iron metal here. Now it is seen that since the energy is quantized means only a certain amount of energy can be absorbed. Remember the island on a man and man on an island and man on a plane analogy, that only a certain amount of energy can be absorbed. So iron metal absorbs some amount of energy, and rest of those which are not absorbed, they are made to pass through here. Suppose in that process only yellow light and green light is been left, and rest of it is absorbed by this iron metal. So this is just an example. You can take any one here. So let us keep it as a sample rather than taking as a metal. Now suppose that sample is absorbing this blue part and this red part. Okay. Now we will have a detector here. So that detector will show us that, okay, we are only able to see yellow light and green light, whereas rest of the part is black. So so black is already being shown in the background. So rest of the part is black. So this spectra that we are getting is different from this spectra, because in this case, what spectra you will get? You will get every color. So you will get red here, you will get your yellow here. Okay. Then you will get your green here. And lastly, your blue here. Got it? Now, some part of this spectra is being absorbed by the sample. So, this thing that we are getting is the emission, so is the absorption spectra. It is the absorption spectra. I guess it is very clear to you right now. Till this point, you don't have any issues. Now, this sample that we got, it is in the excited state. Okay, it is in the excited state. Why? Because it has absorbed the electromagnetic radiation, which is our white light. Got it? Now, excited means it is in a higher energy state. So I have told you earlier that light is nothing but a form of energy, and you know it very well. It is a form of energy. If you keep lighting a beam on a metal, it will start to heat. Okay, so kind of it is giving energy to the metal or to the surface. Now, since it has absorbed light, which is a part of energy, which is simply a form of energy, it has gone to a higher energy state. Its energy is increasing, so higher energy state, or you can call it as the excited state. Now, what are we seeing in both of this? We are seeing that this adsorption spectra and this emission spectra is giving a range of colors. So, I have shown only green and yellow color for example. There can be a range of colors and some part of may be absorbed. But what we need is a specific color. What we need is a specific color. For that thing, what we have done, we have taken the element in which we are interested in the gaseous state. Now, the interesting thing about the gaseous state is that, so suppose we take iron metal, same iron metal, but in the gaseous state. Now, this gaseous state has a special property that it will only absorb a single light, not a range of colors. So, you will not get a spectra, but you will get lines instead. Okay, you will get lines of spectra instead. Okay, so we will not get this kind of spectra and then this kind of spectra. Instead of that, so if you are getting yellow and red light, you will get simply lines of yellow and red. So that is the difference between the normal spectra of the sample and the gaseous spectra. Now this spectra is called as the atomic spectra, in which we are getting lines. No, that can be a single line of one color. Okay, of two colors, three colors, that can be a combination of that. But we won't get this type of thing, that there is yellow spread through an area, then blue spread through an area. You will not get this. Instead, we will get yellow in a single line, blue in a single line, in that way, right? So that is the difference between normal spectra and this atomic spectra. So that this same thing is been mentioned here, that the emission spectra of atom in the gas phase, on the other hand, do not show a continuous spread. It is not spreaded, but rather than it is giving a straight line called as the line spectra or atomic spectra. Got it? Now the interesting part is that some of the elements are discovered using this spectroscopic method. So it was seen by the researchers that these three materials are giving a spectra that is not registered in their book. So they must having a set of atomic spectra for different elements. So for these, while discovering these elements, they got new type of spectra and they named them as different elements. Okay, so this is just for your knowledge. So this is about the line emission spectra. Now we'll need to quantify it. So this part is very, very important, which is line spectrum of the hydrogen atom. So what are we saying? That we were exciting our metal using the light, but here we are exciting our hydrogen atom, hydrogen molecule, with the help of electric discharge. So electricity is also a type of energy. So two things are there while discovering anything. that is quantifying and qualitative, quantitative and qualitative. Suppose you are mixing sugar in water. So mixing sugar in water, you know that sugar and water are present in the solution. So that is a qualitative assessment, means you are judging the quality. But if I ask you what amount of sugar is dissolved in what amount of water, that is a quantitative assessment. So now we are moving on to quantitative assessment. So we are interested in hydrogen molecule. Okay. So again we are applying energy to the molecule to make it go into the excited state. But in this case, rather than applying it through the say electromagnetic radiation, we are applying this energy through the electricity. So electricity also a form of energy. Now when we do that, it goes into highly excited state, and in that process, of course, it will absorb frequencies or light. Got it? Now when it emits different spectra, since your hydrogen molecule is in the gaseous phase, we will get the atomic spectra of the hydrogen molecule if we excite it. Okay, so in this case we are doing the emission spectra. We are interested in the emission spectra. So there can be multiple number of wavelengths that we will get depending upon the energy that we have excited the molecule. Suppose different transitions can be possible. So we will see those transitions one by one. So electric discharge is not giving colors. Okay. So it is giving energy to the hydrogen atom. After taking that energy, it is emitting the taken energy in the form of light. Okay, it is taking energy in the form of electricity and emitting energy in the form of electromagnetic radiation. So these are the spectral lines that we can get. So for one hydrogen atom, there is one electron that is present. Now, this one electron should be present in the first state where n is equals to 1. We know it very well. The K shell where the electron should be present. That is the most ground state for that atom. Okay. Now, after absorbing energy, it will go to a third state, to the second state and fourth state. Any state it can go. And then it will come back. So what are we interested in? We are interested in the coming back of that electron. So during the emission spectra, what happens? First, our sample is excited using energy. In that case, the electrons present in the sample goes to an excited state. Now when it comes back, the same thing, I am depicting it one more time. When it comes back, we take that energy and keep it on a detector which is radiated in the form of electromagnetic radiation. Now suppose after excitation with the help of this electric discharge, the electron has gone to the state 1. Okay, has gone to the state 2 or 3 or 4. After this emission of light, the electron will come back to the ground state. So it can come from 2 to 1, from 3 to 1. So whenever the last state where the electron is coming back is 1, then we call it as the Lehman series. Okay, I am repeating it one more time. Suppose we have excited the sample. In that process, the electron has gone to the higher energy. So if first is the ground state, then second, third, fourth and so on is the higher state. Now it will come back. So it can come back to second, fourth, anyone. So if it is coming back to the 1, then we call it as the Lehman series. Now it can come from 2 to 1. So that will give you one color. From 3 to 1, that will give you another color. 4 to 1, it will give you another color. Similarly, we have Balmer, where electron is coming from any higher excited state to the second state. Then third is for Paskin, fourth for Brackett, and 5 is for Pfund. Now in this process, we will get some light spectra. It is also possible that the spectra that we got may not fall in the visible region. So for example, We will get spectra for the Lyman series in the ultraviolet rays, for Balmer in the visible rays, Pascal infrared, bracket infrared, and Pfund infrared. So the only part that we see in the visible region is the Balmer series. Now, if this thing is not clear, you will see one diagram that will make things more clear. So this is the diagram. So what we have done initially, we have excited the electron. Now it may go to the second state, to the third state, to the fourth state, to the 5, to the 6, to the infinity one. Okay. Now on coming back to the ground state, it can come on to 1. So there can be multiple transitions now. Suppose our electron has gone to the 2 and it is coming back to the 1. That will lead to one line. Suppose our electron has gone to the third excited state upon excitation. Again, it will come to the 1. So the series that we are getting on coming on to the 1 is called as the Lyman series, and it is falling in the ultraviolet region. If the excited electron is coming to the second, n is equals to 2, then it is the Balmer series, then the Pascal, and so on. Remember students, n is equals to 1 is called as the ground state, n is equals to 2 is called as the first excited state. So there is just another name. Remember this name, it's very important. Then n is equals to 3 is the second excited state. And so on. Now, here comes the quantification part that I was talking about. So during this transition, we are saying that our electron or the sample is emitting energy in the form of electromagnetic radiation in the different region of the spectra. That would be ultraviolet or visible or anything. But what is that amount of energy? How you will calculate this? For that, we have a formula. Okay. So we can calculate the wave number of the light or the electromagnetic radiation that we got using this formula, where NF is the final state. So suppose we are talking about Balmer. So in Balmer, every electron was coming onto the 2. So for Balmer, NF will be equals to 2, and Ni can be anything greater than 2 from where it is coming. Okay. Of course, it is wave number 1 by lambda. Lambda is the wavelength. So lambda has a unit of centimeter. So wave number have a unit of centimeter inverse. Now this 109677 is known as the Rydberg constant for hydrogen. So if I want to calculate the wave number, we will use this formula. But if I want to calculate the energy difference between those two states, then that will be calculated using this formula, where our first part is only changed, rest of the part is as it is. Now what is the meaning of this delta E? It's important here. So when we are going from a higher state to a lower state, then that electron is emitting energy. Okay, it is emitting energy. So this energy must be equal to the difference between these two states. Okay, suppose here the energy is 10, here the energy is 5. The amount of energy or the light that is emitted should have an energy of 5. That should be true. Okay, then and then only this transition will be possible. It's very important to note this point. Suppose our electron was in the energy state where its energy was 10, and in the ground and the final state it is 5. So it emits light during this transition. So this transition will have some electromagnetic radiation, and that radiation will have an energy of 5, which is the difference between these two. Yes, it is losing energy in this process. This electron is losing energy in this process so that it can go to a lower state. Because if it is emitting electromagnetic radiation, that means it is losing energy. Okay, it's very clear, I guess. So you can also say that if it is suppose NF, sorry, this is Ni, this is NF, then this 5 amount of energy that is released, it must be the energy difference between NF and NI. Now next part, it is very important. Questions are asked from here. Multiple times questions are asked from here in the NEET and JEE exams both. Including that formula. This formula is also very, very important. Now what it gives us the number of spectral line. What is the meaning of this? Suppose we have an electron in the second excited state. That means n is equals to 3, n is equals to 2 is the first excited state. So our electron is in the n is equals to 3. Then it moves to the ground state. So in this case, n will be equals to 1. So when we will do questions on this NEET and JEE PYQ, you will see the example of this same question. It was asked to calculate the number of spectral lines. So in the second excited state, n is equals to 3, and in the ground state, n is equals to 1. But in this process, there can be multiple transition. So first transition may be possible, that if it is in the second excited state, it can come to the first excited state, which is 2. So from 3 it can come to 2. The second possibility is, if it is coming from third to 2, then it can come from 2 to 1. It is very obvious because it has to finally come in the ground state. What is the third possibility? That it can directly come from 3 to 1. So these are the 3 possibilities. So what are the number of spectral lines? It would be 3. Now in this case, it is very easy to calculate. But suppose you are asked that an electron is coming from the 5th state. Then in that case, what will the number of transition? So that is very difficult to understand, because you can have multiple number of transitions. So to just do this thing in a simple way, we have a formula. So what we do, we know that our initial state is the second excited state, which is n is equals to 3, and final state is ground state, where n is equals to 1. So what will be delta n? Delta n means the starting n minus the ending n. So we are starting from the second excited state and coming on to the ground state. So 3 minus 1, that will give you 2. So this is delta n. I guess it is clear. Now put this value of delta n here and calculate the number of spectral line. Without doing this fatigue, you can directly get your answer. Is this point clear to all of you? So it's very important to understand this thing. Okay. So again, I'm repeating it, from second excited state, there can be multiple transition. It can go from 3 to 2, 2 to 1, or it can go from 3 directly to 1. If you're starting from 4, then it can go from 4 to 3, 3 to 2, 2 to 1. Now that is very difficult to calculate. So simply use this formula. The initial state minus final state, that is n2 minus n1. Put this here, delta n into delta n plus 1 by 2. And that will directly give you the answer. Now here is a question for you. So I am moving on through this question quickly. We are lacking time. So we have a 100-watt bulb that is emitting a wavelength of 400 nanometer. So we have to calculate that what is the number of photons emitted per second by the bulb. How we'll solve it? We know that the power of the bulb is 100 watt. What does it mean? So we know that power is also simply joule per second. That means it is emitting 100 joule of energy per second. Now, what is the energy of one photon? Very simple to calculate. Use the wavelength formula. Just put the values here and you will get it as 4.969 into 10 to the power minus 19 joule. So we got the energy of one photon. Now what will be the number of photons? That would be simply 100 joule divided by the energy of one photon. So 100 joule is the energy that is emitted per second, and this much amount of energy is emitted by one photon. So what is the number of photon? Simply use the unitary method, divide these two. You will get this value as 2.012 into 10 to the power 20. So per second, this much amount of photon is released. Now we will see the Bohr's postulate. So we will start now the Bohr's model for hydrogen atom. The postulates are very important. We will go through each of them one by one. First is that electron in a hydrogen atom. So this is specifically for hydrogen atom. He says that electron revolve around the proton in a fixed orbit. Rutherford did not say that. He said that it will revolve around in a fixed orbit. He named them as orbit stationary states or allowed energy states. And these orbits are arranged concentrically around the nucleus. Concentrically means, suppose here is your nucleus, then we have first shell, second shell and third shell. So this is called as concentrically. Clear? Second thing is, whenever our electron is revolving around the orbit, it will not change its energy with time. So its energy will be fixed. It can only change its energy when it will go from a higher state to a lower state. Okay. So two things are there, that electrons can only revolve in a certain orbit, and second thing is it cannot change its energy with time. If it is changing, then it has to go from a initial state to a different state. So that is very true. What is the third postulate? Now during this transition, during going from one state to another, we have seen that electrons emit energy. Now if I represent it with the delta E, then the frequency of that light can be given by delta E by H. Delta E is simply energy of the final state minus the energy of the initial state. Okay. So by this formula, you can get the frequency of the light that it emits, where E1 is the energy of the lower and E2 is the energy of the higher allowed state. This point is very, very important. It says that electron can only revolve in those stationary states where its angular momentum is equals to nh by 2 pi. Now this is very, very important. It says that suppose an electron is revolving around a nucleus, it must have an angular momentum. Okay. Now that angular momentum must be equal to integral multiple of h by 2 pi. Okay. Now this n can be any integer, 1, 2, 3. So what we can say about the Bohr's theory, that so upon taking those assumptions, he arrived onto some results. So first is the stationary state that we are talking about, they will have a value of 1, 2, 3 and so on. Now these are integer number and they are known as the principal quantum number. Second thing, if you want to calculate the radii of that each stationary state, you will use the formula Rn equal to n square a naught, where n is the value which will come from the number of stationary state and a naught has a fixed value of 52.9 picometer. So it is very obvious, as we go on increasing the value of principal quantum number, the radius will increase continuously. Then the third point, each orbit will have its energy. So that will be given by the formula En is equals to minus RH 1 by n square, where n is again the same quantum number. So if you want to calculate the energy of a given state, then just simply keep the value of that state and take this RH, that same RH that we have seen here. But here you will take that RH in terms of energy minus 2.18 into 10 to the power minus 18, that value, not the wave number value. So its value is 2.18 into 10 to the power minus 18. So suppose if we are calculating for the first state, just take 1 by 1 square instead of 1. For second state, just take 1 by 2 square and you will get the corresponding energy of the given state. Now we are getting a negative value of energy. What does it mean? So we are getting for the first ground state energy as, so here we have written it in terms of electron volt rather than joule, here also and here also. But when the electron is at infinity, its energy will be 0 because the formula was 1 by n square. So if we take the square of infinity and take its reciprocal, 1 by infinity will give you 0. So the energy at the infinity distance will be 0. Here the negative sign is indicating that the energy of the free electron is higher and the energy of the electron that is bonded to a nucleus is lower. Okay? And it is lowered by a certain amount. So if it is at the ground state, it is lower by minus 13.6 electron volt. If it has n is equals to 2, then the energy is lowered by minus 3.4. So what we are doing here, we are just using the formula of the energy and calculating the energy, and then what we are doing, we are converting it to the electron volt. Just simply multiply that value, that is 2.18 into 10 to the power minus 18 by 1.6 into 10 to the power minus 19, which is the charge on one electron. I have already shown this conversion in the first class, the unit conversion, how you will calculate the convert the energy in joule to electron volt. So we can easily say if an electron is present at infinite distance, its energy will be 0 because E is equals to minus 1 by n square into a constant. So if n is infinity, then 1 by n infinity square will be 0. And as the electron will come closer to nucleus, its energy will be more negative. That means it is more stabilized because the attraction goes on increasing between electron and proton. And once the attraction energy is increased, the energy is decreased. Okay, so more the attraction forces, less is the energy. So again I am repeating it. As the electron comes close to the nucleus, so suppose it is at infinity, if it is coming close to the nucleus, means it is under the influence of a attractive force. So if a system is there and it is having more and more attractive force, that means its energy will decrease. So as it is coming closer and closer to the nucleus from the infinite distance, its energy is decreasing due to increase in the attractive forces. Now this Bohr's theory can be applied not only to the hydrogen but also to the hydrogen-like species. Now what is the meaning of hydrogen-like species? Suppose you are taking helium and taking one electron out of it. Then it has the same number as the hydrogen atom has, same number of electron as the hydrogen atom has. So it can be called as hydrogen-like species. Similarly for the lithium and same thing for the beryllium. Now in that case the formula is changed a little bit. So we simply take z square factor on the top apart from the rest of the formula, where z is what? Z is the atomic number. So if it is helium, it will be 2. If it is lithium, it will be 3. Similarly for the radii also, the formula becomes n square by z. So we divided by z. So here we multiplied by z square, here we divided by the z, where z is again the atomic number. Now how do we derive this formula? This is very important. It is there in your JEE syllabus and in your NEET syllabus as well. So first thing, we know that electrons are revolving around the nucleus under the electrostatic force of attraction. And it can only revolve around those nucleus in those orbits whereas angular momentum is quantized, means certain angular momentum are allowed, which is integral number of h by 2 pi. So we can say it from the previous equation that MBR is equals to NH by 2 pi. Then what is the next thing? Now, if it is revolving around the nucleus, then this thing should be true. Two types of force will act on this. First is the attractive force towards the proton, and second is the centripetal force. So if anything is revolving in a circular orbit, it will experience a force outward. Okay, and that force is called as the centripetal force. So you can see it in the physics. Its formula is mv square by r. Now for a definite rotation, this and this force should be balanced. Then only your rotation is possible. So what we can say, k square by r square is equals to mb square by r. In general, we can take z also. We have seen that the formula is changed by z because z is including the number of protons. For hydrogen like species, we have greater number of protons. Here k is the Coulomb's constant, so this is directly from the Coulomb's equation. E is the charge on electron and z is the atomic number. For hydrogen it will be 1, for helium plus it will be 2. Then next, what will be the expression of radii? If we take those two equations, then what we can get? We can get mbr is equals to nh by 2 pi or v is equals to nh by 2 pi mr. Now putting this value of v in the previous equation, we will get zka square by r square is equals to mr multiplied by nh by 2 pi mr whole square. From here you will get the radii of the nth orbit. So this is the complete formula. When you put the constant, you get the final formula. Next thing is the calculation for energy. We know that the kinetic energy is given by half mv square. And here the potential energy is what? It is simply the electrostatic force of attraction. So two energies are there in the total energy, which are kinetic and potential. So we have seen it from earlier that zka square by r square is equals to mv square by r. The balance between the centripetal force and the electrostatic attraction will give you the value of mv square. So what will be the kinetic energy now? Half kze square by r. Now we can add both of this to get the total energy. So this is your total energy. If we put the value of r from the previous equation, so which is this value, you will get the value of energy. Now next we will derive the expression for velocity. We know again from the quantization of energy, v is equals to nh by 2 pi mr. Then from the equation, mb square is equals to zke square by r. Or we can write v square is equals to zke square by r, where by mr, where we can get the value of v. Now if we substitute the value of r that we got in the previous equation in this here, then we can get the velocity also. If you put it, you will get the Rn value this. Just put it in the velocity equation. You will get your final velocity. Okay, so this is the final equation. Now, just put all the value of constants and you will get your radii final equation. So this is the radii that we will get. 5.29 into 10 to the power minus 11. So this was the value that we were getting earlier. Now it is in meters. Second thing is energy. So just put the value of constant. You will get the energy equation same as the previous one. And third is the velocity, which is Vn is equals to 2.19 into 10 to the power 6 z by n meter per second. Remember the relation between each of this. So z here is the atomic number and n is the value of principal quantum number. Now, with the help of this equation, he also gave the explanation for the spectrum of hydrogen. Now I know it is a bit faster for you, If you have a doubt, you can join the live doubt session also. Maybe there you will get the idea that what is happening if you have a doubt till now. Okay, and go and visit the website to watch the lecture once again. So we know that energy of any state can be found out using this formula. Just put the values of the both of the state and you will get your final formula for the calculation of energy difference. Okay, similarly you can do it for the frequency, okay, and for the wave number. So these are the three most important formulas. Now these formulas are same that we got in the previous slide. Okay, so this was all for the today's lecture. Thank you.